wanted to investigate whether ships are spending more time in the marginalized zone in recent years, given the increase in ships in the region over the last 10 years. We also wanted to know where ships are encountering the marginalized zone, and are those locations where ships are engaging ice, are they consistent or predictable over time, which would be conducive to effective emergency planning. So this is the study site that we chose. It's all latitudes north of 66.5 degrees, so it approximates the Arctic Circle. We chose to focus on the month of September because, of course, this is the month with the minimum sea ice coverage and the maximum maritime traffic. We focused on the years 2012 to 2023 simply because this is where a lot of where the satellite-based ship data are available and also quite reliable as well. So we used for our analysis ship data downloaded from the Global Maritime Traffic Density Service. So this is a recently available, publicly available source of satellite-based AIS information that is available for anybody to download. It's a service that's the result of a partnership between the US National Geospatial Intelligence Agency and a company called MapLarge. So the data set actually provides global spatial coverage for AIS data. Of course, we narrowed that down to our study site. The temporal resolution is on the order of 1 month, so it was conducive to our interest in September. Posed a little bit of a challenge with respect to sea ice, I'll mention in a moment. But the metric that the data set provides is ship hours. So a little bit different from the number of individual vessels or the distance sailed that some other authors have used. So this is ship hours that we're going to be looking at today. We downloaded sea ice data from the US National Ice Center. So the National Ice Center provides daily sea ice files, and this is an example of one day, September 1st, 2023. And we basically characterize the polygons into areas of open water, marginal ice zone in purple, and pack ice in white. The challenge is that the marginal ice zone and pack ice is dynamic over time, and so the little animation that's going down there in the corner of the screen shows pack ice and marginal ice zone over the 30 days of September 2023. And so because the ship data was binned by month, we had to bin somehow the ice data by month as well. And so we developed this metric shown here. The blue continues to represent areas that were always open water, the white areas that were always pack ice, and the purple indicates cells, 10 square kilometer cells, that were covered at least one day by the marginal ice zone. The light purple indicates areas that transition during the month between open water and marginal ice zone, and the dark purple are areas that transition between marginal ice zone and pack ice. So we created these monthly maps for sea ice in each September over the last 12 years. And we coupled that with the ship hours. And this is the type of data set then that we conducted the analysis on. You can see the sea ice there for September 2023 and ship hours, with a lot of ship hours next to the coast. And you can even see some ships spending some time in the marginal ice zone and also in the pack ice. I should say that the ship hours data set that we used, again, this is an initial look at where ships were interacting with ice. So it combines all ship types, and we recognize that ship type is extremely important, and it might be a next step for the studies to divide these into different categories. But we're going to be looking at, except for at the very end, all ships combined. All right, so moving on to some of the initial results. This is just generally like lay of the land. What is happening out there with the marginal ice zone and also ship hours? So the top graph shows changes over the 12-year period in the spatial extent of the marginal ice zone. There's a lot of interannual variability. We didn't really necessarily see a directional change in the spatial extent. Definitely not the case for the ship hours. Ship hours increased significantly over the last 12 years, in an increase from 2012 to 2023 on the order of 385%. And that's consistent with other studies that have looked at changes in vessel traffic in the region. So we wanted to know next where these ship hours were taking place: in ice, in open water, And so the middle graph on the slide shows the same graph that we just looked at with black bars, but now the hours are color-coded for whether they occurred in open water, marginalized zone, or pack ice. These bars are mostly blue, which means most of the ship hours, as we would expect, occurred in open water. Because it's hard to see the ice hours up at the top of these bars, I've just plotted separately the ship hours in ice in the graph on the right. And these bars are mostly light purple. So ships that were spending time in ice-prone water were spending time in water that transitioned between the marginalized zone and open water, and not so much time in the dark purple zones or in the pack ice. If we were to plot this on a scatter plot and add a trend line, we would see that there is a positive trend in the number of ship hours in ice over time, but there's a lot of interannual variability, especially if you look at 2019 or 2020. It's not all that predictable. So we were wondering what could be contributing to the interannual variability in the hours that ships are spending in ice. And of course, the most intuitive thing is maybe it just depends upon how much ice is out there. So we correlated the number of ship hours in the marginalized zone with the spatial extent of the marginalized zone, found a positive relationship. There is a lot of variability from year to year, but generally it's a positive relationship. And that seems quite intuitive and maybe not all that interesting to start, but I think it's important for a couple of different reasons. One is that it suggests that there's not a wholesale avoidance of ice up there, that when there is ice around, ships are engaging it. Of course, maritime sector matters, but again, this is all ships combined. It's also important because some authors have shown an increase in the spatial extent of the marginalized zone over time, and even increases in extent to continue over the next couple of decades. And if that's the case, then we might expect more ships to be spending more time in the marginalized zone in the future. But as we started to interpret some of the data that we were looking at, we became a little bit concerned that maybe we were overestimating the amount of ship hours that were spent in ice-prone water, primarily because of that binning over a monthly scale for the ships and also for the ice. For example, it was possible, worst case scenario, that ice was present in a grid cell on one day, say September 1st, and the ships passed by on September 30th, and we were calling that ships in ice, and that really wasn't the case. So we used some data we had access to from the Coast Guard Navigation Center for a small portion of the study site in 1 September in 2021. So we could really drill down on the relationship between ships and ice, and it allowed us to match ship locations with ice on a daily basis. So now we're minimizing that potential temporal gap from 1 month down to 1 day. When we did that, we found that in this area over these 30 days, there were 196 different unique vessels in this area, and about almost half of them spent at least some time in the marginalized zone, about 7% in pack ice. So we felt a little bit more confident in our monthly binned data set going forward in the analysis, that at least the GMT, TDS, and monthly sea ice data set were providing a reasonable measure of ships in ice-prone water. So I'll move on to the second question that we had about where ships are operating in ice. And so we developed first this map, which you can see represents just ships operating in ice as we had defined it. Notice that a lot of the ships' hours that you saw on the previous map originally operating along the coast are all removed, so now these are just ships operating in ice. These are also the 12 years combined, so it's a big kind of amalgamation of ship hours from all ship types. But it gives us a look at, over the last 12 years, where are ships operating. And I have to say I was a little amazed when I first saw this map, because I had sort of imagined ships operating around the fringe of the sea ice edge, but no, actually ships are operating in the presence of ice across the Arctic. There are a couple of areas where ship ice hours are 0 or low, including the Barents Sea during September, where there may be a lack of ice, and then also north of Greenland and north of Canada, where where ships are sort of avoiding the thickest multi-year ice. Okay, so one of the first thoughts we had about this particular picture is that it really highlights the widespread nature of ships operating in sort of risky conditions. And we feel like it also highlights very much so the importance of international cooperation when it comes to preparing for ship and ice encounters. So these are the boundaries of the areas of responsibility for the 2011 Arctic SAR agreement. We just point out that all parties to the agreement share interest in preparing for and making sure they're ready for effective responses to search and rescue or maritime environmental response when it comes to ships encountering ice. We also highlight 5 different areas where ship hours were high over this time period, and so I show them there in the red box. These are the areas where we had envisioned might be really important areas that could help to prioritize emergency preparedness, right? These are areas maybe where you might focus on revising and updating your geographic response plans, or citing interagency exercises, or even staging assets. So these areas might be especially good for those types of endeavors if the number of ship hours in these red boxes was consistently high from year to year. So our next question was, are these locations consistent over time with respect to ship-ice interactions? Or are these red zones really just representing one year where ship ice hours were really high, but actually ships are encountering ice at different frequencies all across the Arctic? And so to look at that question, we broke out the number of ship hours per year for each red box, and we found that it was actually quite interannually variable. There were some years when there were very few ship ice hours in some of these zones, and some years when suddenly the number of ship hours in ice would really shoot up. And a good example of that is the East Siberian Chukchi and Beaufort Sea down here in the lower right. But all of the locations have situations of high interannual variability. So going back to our original idea, of course, maybe it's just a function of how much ice is around during that particular year. This interannual variability would make it hard, though, for emergency planning or staging if it was difficult to predict whether it was going to be a large bar, right, or a short bar. And so we did our little correlation analysis again with the amount of ice cover in each red box relative to the ship ice hours, and we found a positive correlation again in each case. But there was a lot of variability in the strength of that correlation depending upon which location you were looking at. For example, if you look at the Vilkilsky Strait, the correlation is very strong. The R-squared is about 0.86. So in these cases, it looked like ships were operating through the strait, regardless of what the ice conditions, if I could sort of overgeneralize for a moment to make the point, they were operating regardless of the ice conditions. As opposed to Northeast Greenland, where there was a positive relationship, but it was a really weak relationship. The R-squared in this case was 0.16. Meaning that ice coverage played some role, but there was probably something else at play. And it could be a number of different things that would be interesting to look into. Maybe there are different types of ships involved in this correlation in Greenland versus maybe cargo vessels, for example, along the Northern Sea Route that might have a different mission, right? And might be less ice averse. Okay, so we did pull out a couple of ship types that are of particular interest with respect to safety, not only of human safety and mariner safety, but also safety of the environment. We started with fishing vessels. So fishing vessels tend to account for a relatively large number of accidents at sea, including in some of the Arctic data sets that we've taken a look at. And so we wanted to know where they are interacting with ice. So shipping vessels overall accounted for a good third to about I guess I should look at the slide, right? About a 20th to a third, or a fifth to a third, thank you, of the total ship hours overall, but they accounted for less than 1% of the ships in ice. So very, very little ice interactions with fishing vessels, which is good news. I would be happy to address, I see I'm getting a little short on time, so I'd be happy to address the graph on the bottom maybe afterwards. But you can see that their numbers are increasing in this region over time as well, and they spend most of their time in open water. The second vessel type that we pulled out separately was tankers because of concern for the release of liquid cargo like oil or other type of cargo that they might be carrying. Their numbers increase over time, but it's sort of the opposite pattern of fishing vessels in that they accounted for only 2 to 5% overall of the ship hours in the study site, but about 8% of their hours were spent interacting with ice or in ice-prone water. So to conclude, we probably created more questions than we actually answered through the study, which is always fun and means that we would love your feedback on what might be interesting to you in terms of what directions might be most useful in terms of emergency planning and preparedness in the Arctic with respect to vessels interacting with ice. So overall, we found ship hours increased since 2012 up there, an increase quite significantly on the order of 385%. We found that if the marginal ice zone coverage continues to expand as predicted, that we might have more ships interacting with ice in the future, and we need to prepare for that. Finally, ship ice hours were also very widespread, particularly near the coast in the East Siberian, Chukchi, and Beaufort Seas. And some authors have found that this area is experiencing delayed freeze-up over the last several years. And if that's the case, and more ships tend to spend more time in September around this period and in this region, it may be problematic in years of especially early freezes or early freezes. That was linked to this large besetting event of between 80 and 20 different vessels in November 2021, was an early autumn freeze-up. My last slide, just to conclude with respect to the areas of high ship hours in ice, those red box areas, we're very interested in knowing whether the accident databases support these areas as being high risk for ships in ice. And so we have taken a look at what is out there from PAIM, which has been especially useful, but we welcome ideas for other data sets on maritime accidents that we might be able to isolate some of those accidents that were associated with ice collisions or besetting to see whether they fall in those red box areas or actually we're on the wrong track and should be thinking about something else with respect to risk relative to vessels operating in ice. Finally, we're interested in what the role of seasonality is. These globes down here, it's the same study site that we did our study, showed for 2023 variability over the year in pack ice, marginal ice zone, and open water. And we're particularly interested in the spring season, which seems to show a lot of variability in the marginal ice zone. Perhaps the risk landscape looks a little bit different during spring. And with that, I would just like to say thank you, and I hope to address any of your questions. Thank you.
Thank you, Lucy. That was good. And I gotta, why is this important to me? It's important to all of you. And I don't think I mentioned, so I am the expert group chair for search and rescue in EPPR. I feel like I'm a student right now, and I'm absorbing all kinds of information. I think one of the presenters said, I'm inhaling the science. And well, I am inhaling the science. So I'm learning a lot. We'll still, if you don't mind, we'll hold questions for the end. But I got questions, and hopefully other people do as well. Full disclosure, our next presenter, Dylan Jones, I participated in the research. I think I'm supposed to say that, Penny. Am I supposed to say that or not? Is it a conflict of interest? I don't think it's going to be a conflict of interest because Dylan's going to give his presentation anyway, and we had a lot of fun working together. So without any further ado, here, I have to introduce you properly. Dylan Jones with a big, warm Graham Norton welcome. Woo!
Right, thank you, Ben. And if you recognise yourself in any of the pictures, just wave. You'll see. Okay, this is an update on the ArcSAR project, which I shared about at this conference last year. It's by myself and colleagues from the Centre of Operational Research and Logistics at the University of Portsmouth and Miguel Dominguez at JRCC in Norway. Okay, if you are unaware of the ArcSAR project, it has been running for a while now. It was funded under the Horizon 2020 frameworks, and it's just about to come to an end at the end of February, having run since 2018, been extended because of the pandemic. So Ben, myself, and others, I think we had the honour of being one of the few people still working on a live Horizon 2020 project. Its aim was to look at the security and safety challenges that may be arising because of the opening of the sea passages, and we've seen some great presentations already in this stream that have been quantifying this, including the last one, and it's clear to see that there is a rise. Obviously, things have progressed as we've gone on through the project as well, and new situations have arisen too with respect to the safety and security landscape. And it's looking about what innovations, particularly in maritime SAR, search and rescue, and marine environmental response, we should be looking at doing in respect to those challenges. So what I shared last time, and I'm not going into great detail because this is the result of the early years of the ArcSAR project. So this was a result of a lot of liaison with experts and various workshops and questionnaires, expert opinion, and some mathematical optimization to work out exactly, classify and prioritize the innovation needs according to class. There were about 75 different identified needs for innovation in this field, but as suggested by our EU reviewers, that we concentrate on around the top 20%. So you see them there, and I'll show you the reference if you want to see it in more detail, onto 6 polar need main categories that are inspired loosely by the IMO Polar Code. So you'll see vessels, and this is the code, and life-saving equipment, and cold and sea survival, C for communication, P for pollution and incident, N for navigation, and T for training, education, and personnel issues. So having done this, the next step forward for this part of the ArcSAR project was to have some stakeholder workshops to see how we engaged really from a descriptive point of view, seeing where we're at with each of these needs and the priority sub-need topics with some emerging ones, and to see predictively what might happen in the future and what are the future needs going to be. And the final kind of analytics theme is prescriptive analytics, and that basically means what should we be doing about this? What prescriptive actions should we be taking in response to these needs for innovations in the Arctic? So we had a fairly classic kind of workshop organisation in inviting keynote speakers and doing some SWOT analysis, so strengths, weaknesses, opportunities, threats, and then some foresight analysis to answer the last 2 questions. What might happen in the future? What do we need to combat that? So what you see there is a slightly different part of ArcSAR. It is that's the LiveX exercise that took part in Svalbard in September 2022. and you can see that simulating the evacuation of a vessel of around about 50, and nobody's waved, so I presume that's none of you on the photo, but they are ArcSAR people. But remember that, because it's important for what I was about to say, that there was about 50 people on that ship that was evacuated. Then the 3 workshops, you can see the SWOT analysis there. The first one in Portsmouth was about how we combine satellite technologies, drones or UAVs, and AI in order to enhance situational awareness when there are incidents spanning across SAR and MER, and the combination, the synergy between those 3 emerging and new technologies and how they should be used. The second one based up in Svalbard, and you can see that this is kind of a link to the geographical location. So it's what capabilities are there in local communities to respond to a major SAR incident. The classic, what we mean by major SAR incident in ArcSAR was mainly either a large cruise ship getting into trouble, a nuclear incident, or a major oil spill were the typical things that we were looking at there. The third workshop in Cork, a lot of the priority needs talked about standardization and the need for standardization, so we had a workshop on that too. Okay, what did we find? Well, I actually have physical copies here, but we have 3, you can see here, workshop basically summaries of the 3 workshops. These are available in hard copy if you want them, but far more practical. You can see the web link on the ArcSAR website where you can download either these and all of our deliverables so far, because I said the ArcSAR project's been running for 5 or 6 years, so this talk is just about one aspect of that particular project. I can't really properly summarize like 75 pages of report in one slide, but I'll give you some of the key findings that I think to pick out from there. When it comes to the first workshop about regulations and protocols, we saw that each one of them had a part to play in situational awareness, but really some of the strength that we found was in the symbiosis when all 3 were working together and those kind of different streams of information being merged. That's where it was thought by the experts to be real benefits. And again, this kind of links into some of the testing that we did in the live exercise too. There was also point out that the technology, it is ever moving, evolving, but also what needs to evolve is the regulations and the protocols, particularly when you're dealing across different territories and nations. That was felt to be equally as important. With respect to the second workshop, and also a lot of the interviews that we have done with SAR experts, there is a need to train volunteers. Really across different territories, we had the same kind of emphasis on we rely on a volunteer base, and we need funds and resources and standardization of training for that volunteer place, particularly when you deal with large incidents in remote locations where there are various gaps. The other thing that was pointed out is that, yes, this is an exercise with 50 people being evacuated on boats from a cruise ship, for example, but that could be 1 to several thousand, particularly going into the future. So larger LiveX, TTX exercises were definitely felt to be welcomed by local stakeholders there. The final one on standardization was interesting because it did say that we needed standardization for obvious reasons across a whole range of topics. However, a level of standardization. The message isn't really meant to be standardize, standardize, standardize at all costs, because some things need to be customized to local conditions and specific laws, regulations, circumstances, for example. So it becomes more of a trade-off of how much is the standardization going to cost, and what level do you do standardization versus customization to local circumstance. And that's really something to explore going forward in the standardization debate. So hopefully with a few minutes that's given you an overview of this part of the ArcSAR project. We will be meeting for our final dissemination event in Brussels on the 21st of February. Details on that website, link arcsar.eu, and you're most welcome to join us there as well. Thank you.
Thank you very much, Dylan. You left out the best part of the ArcSAR deliverables, which is the ArcSAR movie. And the movie can be found by going to YouTube and just Google or YouTube ArcSAR movie or ArcSAR, and you'll get, it's a fantastic, fantastic movie. But I'm eating up Claire's time, and so we can reminisce about ArcSAR at the free drinks later. Claire Bernard Grandmaison is here and is up next, and I'm keeping close to time, and I'm letting the speakers introduce themselves because I won't do them justice. So the floor is yours. A big Graham welcome. Woo! Thank you.
Great. Hi, everyone. Good afternoon. I'm a geospatial analyst at Equinor, and on behalf of my team of the Johan Castberg project and our licensed partners, I'll be giving you a quick overview of the ice risk management system we have been developing. So first, let's start with some context. All okay? No? Thank you. That's better? Perfect. Okay. Some context. The Johan Castberg field is located approximately in the middle between northern Norway and Bear Island in the southern Barents Sea. It will be the northernmost field in the world in oil field and gas field in development, and it's planned for startup operations at the end of 2024 for a lifetime of 30 years. The concept is a ship-shaped FPSO, which stands for Floating Production Storage and Offloading, that will be permanently moored to the seabed. Equinor has committed to implementing an ice risk management system at Johan Castberg, and that means that the ice conditions will continuously be monitored. And that's mainly because the probability of sea ice and icebergs coming at the field are low but non-negligible. And following regulations for oil and gas activities in Norway, we need to implement the ALARP principle to reduce risks, which means to reduce risk as low as reasonably practicable with technical and operational solutions. There's also governmental regulations in Norway that prevent drilling closer than 50 kilometers to the observed ice edge at any given time. So what are these risks? Low but non-negligible. The return period for sea ice and iceberg at the Johan Castberg field is on the order of 10,000 years. So that means very, very unlikely that this happens. The last time it was around 100 years ago, but that was also in a colder climate period. The FPSO is designed to withstand these ice loads for these 10,000 years return event, but the estimations of these loads are quite uncertain. So that's why implementing an ice risk management system will contribute to further reduce the risks, and that's aligned with the ALARP principle I just mentioned. We have established clear operating limits for ice. So for sea ice, if it's forecast to reach FPSO within 3.5 days, or it passes the 73 degrees north boundary, you can see that the FPSO on the map is quite far from the marginal ice zone as defined in the Norwegian management plan for the Barents Sea. And for iceberg, regardless of size, if glacial ice is confirmed by visual observation and comes within 12 nautical miles or approximately 22 kilometers from the FPSO, then the limit is reached. And that means that we need to start mitigating mitigation actions, and it's mainly to stop the production, to unman non-essential personnel, and to orient the bow towards incoming ice to reduce probability of impact. So let's dive into the system itself. We are developing something for 30 years, and that makes it a challenge, but that's also what makes it quite interesting to work on. And this system is based on our experience supporting drilling operations in the Barents Sea in the last 10 years, but also on lessons learned of other operators operating in ice. There's 4 main components that follow the OODA loop. So first, let's start on the top left. It's observe, so with surveillance to know where is the ice and where it's going, where it's forecast to drift. Then orient through the decision support system where the threat is assessed and the data is visualized. And that enables the operator to decide and act, so either to increase surveillance activities if ice is moving closer, or to stop the production if the operating limits are reached. And the bottom 2 components are very important to prepare to ensure the OODA loop is well functioning. And it's documentation that enables clear roles and responsibilities at all times, and also training, so the personnel are aware of the risk, the system, and they know how to act in case of ice threat. We have all the technology available today to implement this system, but we know that in the next 30 years, there will certainly be new technologies coming up available to us, cost-effective, especially in the surveillance domain. So all these 4 components, we foresee that they will be enhanced with new technologies, but the system, as you see now, should remain the same for the operating lifetime. So which technologies are we using for ice surveillance? For detecting and tracking ice, our strategy is to use multiple platforms at different scales. And that goes from satellite images at the wider scale to the marine radar on the FPSO. And that's to ensure that no ice comes close to the FPSO undetected. We have many collaborators for the technical solutions, so I'll go through that. For icebergs, we have detection in satellite images they are providing us daily, up to 350 kilometers away from the FPSO. And these object detectors could be iceberg, but can also be false detections. So we need to use other methods to validate if these are supposed to drift closer. For sea ice, it's a bit easier because we know where it is. We have validated products, so the sea ice charts from the Norwegian Ice Service. And if sea ice comes close or there's potentially a large iceberg, we plan to request surveillance from aircraft from NOFO. And they have aircraft equipped with imaging radar and infrared cameras. But mainly at the medium scale, we will use the vessels that are stationed at the FPSO to task them to go out and scout ahead to confirm or infirm if there's ice, and tracked also with their marine radar. Something to mention that all ice observations we will make, we plan to share with national agencies for the safety of other maritime users. For forecasting, for Sea Ice Edge, we're relying on multiple models, but we're also relying on the Barents 2.5 model, which is a high-resolution model that was developed by the Norwegian Meteorological Institute within SURFA, which was a successful research program that was hosted by the university in Tromsø and in which Equinor was a partner. For iceberg drift, this is provided by StormGeo, which is Equinor's already service provider for weather forecast. And we hope to continue our collaboration with them to display the surveillance data in their weather portal as the basis for our decision support system. A bit more detail about how we assess the ice threat. So we have established 4 threat levels, which are associated with actions offshore. And that's to have a gradual progression from level 0. There's no threat, no ice, it's regular surveillance. And that's where the system should be most of the time, level 0, level 1. Gradual progression to a level 4, which means the operating limits are reached and the production should be stopped. It's an emergency situation. The threat levels are determined by specific parameters that we are monitoring, what we call the operating parameters with surveillance. For example, the distance from the FPSO to the iceberg. And these parameters dictate which surveillance method and interval of observation should be used. So for example, at level 0, we are getting satellite images every 24 hours to detect object. And that's most of the time. But then as we move, an object becomes closer, for example, less than 150 kilometers from the FPSO, then threat level 2 is reached, and we have satellite images every 12 hours. And we potentially send a vessel as well to confirm the ice detection. So the main point here, it's quite busy, is that as the threat level increases, surveillance increases and awareness offshore as well, which is associated with specific actions. Lastly, a bit more insight into what we plan for training. It's a very important component of the ice risk management system to keep the competence alive for the lifetime, to incorporate lessons learned as we go along, and to also incorporate new technologies. The participants will learn about the environment Johan Castberg is operating in, including the ice risks, and they will understand how the ice risk management system works and how they should act according to threat levels. We're targeting mainly operational offshore roles because they are the ones who are responsible for the surveillance and are the ones as well who initiate and execute the mitigation actions. And the format is a theory classroom training with recertification, but there's also practical annual training through the emergency preparedness exercises offshore. We're also targeting onshore support and management roles with a high-level, potentially e-learning training, and that's to raise awareness in these roles because they need to be confident supporting the decisions that are made offshore for managing ice risks. In summary, the probability of occurrence of sea ice and iceberg at Johan Castberg is very, very low. After FPSO design, the ice risk management system reduces residual risk even further. That's in accordance with the ALARP principle. Our surveillance strategy is based on proven technologies and ensures the ice situation is known at all times. Collaborating with national agencies and sharing ice observations with other maritime users is essential for safe, sustainable development in the Barents Sea. Thank you.
All right, thank you very, very much. I have questions if others don't at the end, so I'm learning a lot. I'm jealous because I'm learning so much here today. But without further ado, we have Kelsey Frazier from the Ted Stevens Center. The floor is yours. Big Graham, welcome. Graham Norton, welcome. Woo!
Woo! Exactly. Okay. I want to transport all of us away from the fantastic infrastructure that we have in this part of the high north to the lackluster and poor infrastructure we have in my part of the north. Beautiful place, fantastic people, no roads and railroads and airports that go everywhere. So my name's Kelsey Frazier. I'm the current Acting Associate Director for Research and Analysis at the Ted Stevens Center. My background is mechanical engineering, and if you're wondering how that applies to sea ice, me too. Don't know what happened, fell down the rabbit hole and got a PhD. It's how this works, apparently. So I got sucked into what is going on in the Arctic. How do we plan for the imminent oil spill of doom that we deal with in tabletop exercises and that we're deeply concerned about in all regions? And many conversations that I've had. And the challenge has always been, well, we do have models related to sea ice, and we do have models related to oil spills. But when it comes to what the heck happens to the oil when it's under the ice, that's where we really struggle, at least from the scientific standpoint. So that was the problem that I wanted to tackle in my PhD, which I finished in December, so I'm working on all of my naps. Feeling very good at the moment, thank you very much. But oil under ice became kind of the big question in the room. And I worked for a number of years with agencies across Europe and experts from the US in a very collaborative discussion of what in the world do we do? And this was the question that we came back to over and over again. It was, well, we don't know what the underside of the ice is doing, so we can't figure out how the oil's going to move, so we're just going to throw darts at a wall if something happens, which is not a great answer, at least from the scientific perspective. So developing a methodology became kind of the thing that we thought about, the thing that we were trying to tackle all the time, and what I'm really here to talk to you about today. Now, what did we do in the past? Well, we did have sonar transects that looked at the underside of ice. We have put AUVs out there to look at the underside of the ice, but typically the data that we're getting back is for a very small area. I will know what's going on in like 100 square kilometers for a single point in time. But if you're trying to deal with oil spill response, you need to know what's going to happen in the future. You need to know random situations somewhere in the Arctic where you don't have the ability to throw an AUV out or a couple of fellows from your research program to say, go and measure what's happening here. So at the end of the day, what we needed was not only an ability to model the subsurface of the sea ice, but the ability to predict what that subsurface was going to look like depending on the dominant conditions. So we started with data, like any good research project, and Shell was really the organization that allowed us to have all of the subsurface sonar information that we wanted to have. There was some research that they were required to do by the US government from about 2009 to 2015. They wanted to go up to the North Slope of Alaska. They were going to drill. That didn't happen. But in the meantime, they put all of these upward-looking sonar packages and ice profiling sonar packages in the Beaufort and the Chukchi Sea. And all that data is freely available. It's on the North Slope Science Initiative website, and you can download it and take a look at it at any time. So I had sea ice data. But then, remember, we're trying to predict what's going to happen. Where is that ice going to be either more or less chunky on the bottom? And we got to the point where we went, okay, well, what we need is the surface conditions, because that, in an emergency response scenario, we know what the surface conditions kind of look like. We can pull the satellite data, we can send a plane over it, we can kind of get a feel for what the surface looks like. Is there a connection between the surface and the subsurface? Well, I will tell you that I think that there is. Now, how strong of a connection depends on the type of ice and how long that ice has been there. So for those that are not familiar with sea ice, very chunky on the bottom, not super smooth like lake ice is. And what we found when we took all of the sonar data that we had, and we separated all of that data by the observed ice condition. So what the satellites were picking up and the ice analysts were telling us was the dominant condition. When we separated all of that out, suddenly we started to understand what that subsurface form looked like. Now, most of the data that we have for the Beaufort and the Chukchi Sea tells us that it's log-normally distributed, the surface pattern on the bottom. Very unique characteristics to each one of these ice types. And so over a period of, I think I had 5 really good years of data, we had 36 unique ice types that were observed. And of those 36, 31 of them were log-normally distributed. At least that's what I hope that slide says somewhere. The key here, though, in understanding who cares why is this log normally distributed, who cares that there's an analysis, is that now we can start to build models. Now we can start to predict what might happen. Is it perfect? No, because nobody does anything perfect. At least in my world of science, it's iterative. We do one little baby step and we make advances and it's awesome. So the slide in front of you just shows you which ice types that were observed didn't come back as being log normally distributed. Now, why are some of these not fitting into my pattern? Well, it could be that I didn't observe enough of them. It could be that the resolution of the data was so coarse that by the time I had sonar data from underneath, what was observed on the top had already kind of moved through the domain before the satellite picked it up. So there's a number of reasons why a few of these outliers are just kind of shady. More work. All right, a couple of key takeaways. So at this part in the analysis, before we get to the fun, let's put oil under ice. Okay, not fun. Oil under modeled ice. A couple key takeaways. One is that ice does not come in 2 flavors. It's not chocolate and vanilla. It's more like 31, 36 flavors of ice. And so when I have conversations about ice and ice types, I encourage my fellow researchers and scientists to expound upon, well, what do you mean by first-year ice? What do you mean by multi-year ice? First-year ice is like all the ice we see. In fact, I only saw first-year ice for 5 years. That's not just one form of ice. It's a beautiful kind of rainbow of what we have up in the north. And then seasonality plays an important part. So what we might find in September could be very different than what we find in the spring. And so the conversation, I hope, evolves as we move forward. Okay, we have log normal distributions. We have unique parameters for each of those distributions. Let's throw this into MATLAB and see what kind of cool forms might pop out. Now, caveat, sea ice is not sharp like this. It's smooth, but this is what models look like in MATLAB until you get more and better data. This is what one ice type produced. It gives you kind of a chunky format. This is what another ice type produces. Gives you another chunky format. And so as I move through my slides, because I talked too much at the beginning of this, and we need to get to the really interesting parts, at the end of the day, here was the method we chose to do. We created a surface. In the middle of that surface, we put 1 drop of oil. And we let that drop of oil move around the surface until it couldn't move anymore based off of gravity. So it was looking for the lowest hydrostatic pressure. And then we'd add another drop of oil. And we would keep adding drops of oil until the oil at some point spilled off the domain. And it gives us a unique distribution of what we think the sequestration capacity for sea ice could possibly be. Now, the implications here are that at some point in the future, if there's an oil spill, we know more than 0. I can give you an estimate. Is it perfect? Absolutely not. I wish I could go out and do a lot more measurements. But we were at 0 in conversations. We were at, I don't know. And now we're at, well, we have a guess. So we're going to get better. I hope that the future allows us to do more experimentation. You know, the next step is build this in a lab, do some oil spill testing, see what happens in a flume when you add a current into it. But at least we have one step closer to what do we do when the worst possible scenario happens and we have an oil spill in the Arctic. How in the world are we going to respond? Now, the last point I'll hand to you, since I have no more seconds, I have 0 seconds, is that when we modeled the oil under the surfaces of the sea ice, it didn't touch all of the ice. It only touches like 20 to 40%, and there's a reason why. But I will leave you with that because there's the end, and I'm done. Thank you, sir.
Everybody loves a cliffhanger. Thank you very much. And I will add, and you worked the word chunky in a lot. That was my high school nickname. So, you know, thank you very much. Yeah, very well done. We didn't even coordinate ahead of time. Getting some. But to keep things moving along, we have Anna Karlsdottir from Iceland with us. A big Graham Norton welcome for Anna. Woo!
Thank you so much, and I'm so impressed by all these graphs and numbers and things. But I'm not gonna talk about so much about numbers. A little bit. The reason why I'm here is that I'm hoping that I have a message. So I'm a human geographer, come from Iceland. I'm working at the University of Iceland in tourism, at Department of Geography and Tourism Studies, and I have studied community impact, particularly social impact, infrastructure, capacity, and these kind of things that belong to social science. So I have been trying to work on different studies for about 2 decades. They've mainly focused on Icelandic towns and different communities, primarily Ísafjörður in the West Fjords, Akureyri in the north, and also some more remote communities in northwest Greenland, East Greenland, and southern Greenland. And it has involved both data collection, quantitative data collection and qualitative data collection, and it's been supported by various funders, these different sequences, if you can call it, of work. And the focus has been the North Atlantic region and the Arctic. So I have been very privileged being funded by different programs, among them last IPY NSF funded us for climate-human interaction project, and Belmont Arctic initiatives and the Nordic cooperation. And so I have some timeline, and but I'm a bit frustrated. So that brings me here. The rise of cruise tourism in the North Atlantic Arctic dates really back to the 80s. But we can see in the first 2 decades and onwards this huge rise, striking rise in cruise tourism to many of these regions that I've been focusing on. Here I have just brought some graph from the 80s to 2006 to Reykjavik. That is the most visited port in Iceland. At the end of this period, the number of passengers arriving by cruise vessels were 57,000 that year. Notice that number. I know that in Norway there have been various research studies on community impacts from cruise tourism. Social Svalbard has been much in focus. But what frustrates me is that these have rarely been linked to research elsewhere, let's say Iceland, Greenland. So, and as a human geographer, I ask myself, why? Why are we not linking? Why are we not connecting when it comes to community impact and social impact studies? Now, let's go to next period of cruise vessel visits. The first one on the left is Greenland, and it shows this steep rise in visitors from cruises with a bump in the pandemic period. But what is striking here is that then the year after everything's opened up, we already have a number of passengers reaching the same, almost the same levels as before the pandemic. So, then if you go to Reykjavik, we have the same trend. I mean, Reykjavik alone almost reached the record number of passengers as before the pandemic. And in 2023, 300,000 passengers arrived to Reykjavik, 250,000 to Akureyri. And in the community where I've mostly focused, Ísafjörður, the rate of increase in the period between 1996 and 2013 was 2,200%. And in 1996, only 3 ships arrived. But in 2023, passengers were with crew were almost 245,000. It's a lot in a small community of well, a little bit less than 3,000 inhabitants. And when we go to neighbor places like here in Flåm in Norway, we've also seen this tourist boom of an increase by 400% over a 25-year period, even more maybe. I mean, where is the pain limit? So I'm just going to try to sum up like action, reaction, but not really that. What I see as the main issues of concern from a social science perspective in the first decade of the millennium, and in the beginning of 2000 and the years after, there was a lot of expectations around this rise in calls. And the stakeholder organizations, they were primarily concerned with measuring spendings, employment multiplications, cost by visits, and also very interested in hearing from the tourist what was kind of the interesting thing about the place. And as you can see, they have a sharp geographical idea about their visit to Akureyri in this case. It's from one of the surveys made in, I think, 2005. And one of the most spectacular things they saw in Iceland was Norway. So, but the other things that were of concerns after 9/11 were also port IMO standards, combating possible terror attacks, smuggling and human trafficking. And then these questions of security and possible hazards were also emerging. And at this time, I think there was also an emerging acknowledgement of generally a lack of systematic environmental monitoring, at least compared to Alaska at that time. And then there were discussions about memorandums of understandings between ports of call and shipping lines, or stricter regulations. And also some initial work on code of conducts, for instance, the cooperation between World Wildlife Fund and Svalbard. But you have to keep in mind, in this period, in some of the more remote communities, only maybe 3 to 10 ships were visiting every season. So, yes, this picture, it's interesting. I was among those who believed that post-COVID cruises would run into problems due to lack of passengers. But that seems not to be the case. Humans forget easily, and wilderness and nature has, if anything, increased its attraction value. And I think this advertisement from Princess Cruises on Alaska, that's maybe 15 to 20 years old, says it all. Cruises feel less tedious compared to flights. So that's one of the appeals of this type of traveling. In the end, I'm just going to say that there are a lot of emerging issues. We heard some fantastic presentations here on security and SARS and emergency preparedness, but other things that are really at core and will be onwards are sustainability issues when it comes to communities, social carrying capacity in particular, where is limit reached in terms of receiving number of visitors, and environmental impacts are also something where knowledge has really, really increased. On the other hand, there are also some contradiction trends ongoing. And these are megalomania in ship construction, and then louder discussion on cap and calls while expansion of port infrastructure is ongoing. So at last, I'm just going to say that I'm trying to team up with Norway to make some more comparative studies of this. Let's go away from the spot focus and link ourselves, connect, and make comparative studies in this field. Thank you.
Anna, thank you very, very much, and it's nice to have a kind of a different perspective. I've traveled to Iceland quite a bit. I am not worried about safety or security there. The people will give you the shirt off their back. They're just absolutely wonderful. But those are implications that we have to continue to think about, and they lead into some of the other discussions that we had on search and rescue and oil spill response and emergency response as a whole. So we can't forget either the large or the small communities and the small places that people want to visit in the Arctic. Thank you so much for highlighting that. Now, I'm hoping that Wisla is available online. Wisla, are you with us?
Yes, can you hear me?
Yes. Welcome back.
Perfect.
I'm not Penny.
Thank you so much.
I apologize
Thank you
for
so
not
much.
being Penny. She's near me. Is Penny here? Penny, say hi real quick.
Hi, Wisla.
There we go. We're so glad that you were able to come back, and I will turn the floor over to you. And without further ado, please take it away.
Thank you so much. Can you see my screen?
Yep, we've got it.
Okay, so first of all, I just wanted to thank the organizers to trying and working with me to make my talk possible. This is my third time. I hope third time is a charm. First time I made it all the way to Oslo to find out that I won't make in person to the meeting. And earlier today, somehow Zoom connection dropped. So I'll talk to you about something different that was more topic of the session in the morning or around lunchtime about advancements in terms of modeling and prediction related to the Arctic sea ice and climate in general. I have a team of people that I should acknowledge, but for the sake of time, I'll just move on with the presentation. This effort about developing and using predictions from the regional Arctic system model has been in works and use for over a decade now. So just one brief summary of the regional Arctic system model. If you look at the lower right, it's a diagram showing a structure or the components of the regional Arctic system model, or RASM. And the summary take-home message is it's a regional Earth system model. So it has all the different components, climate model components like atmosphere, ocean, sea ice, land hydrology, stream flow routing from land to ocean. And we also have marine biogeochemistry, both in sea ice and the ocean. And the difference is that we need to have boundary conditions from a global model, either for hindcast, simulating the past to present, or Earth system projections for future projections. The take-home message is that in this modeling framework, we're not using data simulation, we're not bias correcting the results. The results from the model for the past and present can be compared to observations because we're forcing it with the real global reanalysis. And this approach allows us to to create physically consistent initial conditions, which are critical for forecast, especially on the longer time scale that I will talk about my next slides. So first thing, I just wanted to show you that we can simulate extreme events as they occurred or have been observed in space and time. I hope this will play. In 2022, September 16, 17, there was a typhoon Merbok that hit the Bering Sea. You'll see it right about now, the blue dots that went through. They observed low pressure during that time. 16, 17 September was 935 hectopascals. Our model simulation have shown 950 minimum. The strongest winds observed were 91 miles per hour, very strong winds. We had in our model simulation 95 miles per hour. And on the right panel, we're showing with the pointer that was associated, that storm typhoon passage was associated with the flooding along the coast of Alaska, specifically within the northern south, with sea level height exceeding more than 2 meters above the normal level. And that was associated with a very heavy flooding of the coastal villages there. Another extreme events that we have looked at is the extreme cyclone of the late January 2022, which started somewhere in the northern Greenland Sea and ended up in the northern Barents Sea. There's a paper published by Blanchard Wigglesworth et al. In 2021. The left panel was showing basically that minimum or extreme event in the model simulation in terms of the sea level pressure. And on the right-hand side, we're showing the response in the terms of the ice concentration in shading, and vectors are representing model simulated response in the sea ice drift. Basically, strong southerly winds associated with this cyclone have contributed to the redistribution of sea ice away from the Barents Sea, pushed the ice out to the north, and that was reflected with the significantly increased air-sea interactions in terms of wintertime heat release from the ocean via sensible latent heat into the atmosphere, which has some teleconnections to the lower latitudes. Another thing we did is just we compare the sea ice thickness in the model against observed from satellites estimates like ICET for the period of 2003-2008. The left panel is a difference between the RASM and ICET for that March over that period, and commonly used Pyoma's difference against ICET. If you compare the two maps of differences, you can see that RASM simulation of ice thickness compared to ICET is comparable or very similar in terms of the distribution and the quality compared to the Pyomas. We also did comparison of the winter, October, April 2010-2014 cryoset against RASM, and also compared the Pyomas. And you can see that a straight line, the blue line diagonal, it means a perfect agreement between cryoset and RASM, while in Pyomas you have some biases specifically related to a thicker ice. In addition, we also look at the mosaic cryoset 2 SMOS estimates, a similar scatter diagram of the sea ice thickness for the winter of 2019-2020. And on the right panel, in the lower right, we're showing the same thing from RASM. So you can see that the spatial distribution and the distribution scatter plots is very similar. The upper right plot is showing comparison of the sea ice drift anomaly on the left from the model, and on the right from the satellite-derived data. So this is all discussed in a paper by Detlef and Maslowski in Cryosphere 2023. Next thing we do, since 2019, we've been using the NCEP National Center Environmental Prediction reanalysis and forecast. On the left is showing the initial conditions from the CFSR sea ice thickness, and the RASM initial conditions are shown for the same April 1, 2017 in the middle. The cryosat estimate for the similar period is shown on the right upper plot. So you can see that RASM and cryosat has a reasonable agreement in terms of ice thickness for that date, versus the CFSR initial conditions from their analysis look very unrealistic. 6 months later, when we look at the forecast from the reanalysis from the NCEP CFS2, you can see that a thick ice that was prominent in the Western Beaufort Sea still remains there 6 months later, versus in RASM simulation, lower middle plot, we have quite a good agreement against the, again, cryosat 2 estimates while using a different shading scheme. This is a screenshot of our RASM website. The website address is up in the upper right panel here. The red dots are indicating observed estimates of the ice extent, and the blue line, solid line, is the multi-ensemble mean, 30 ensemble member mean forecast initialized on April 1, 2023, forecasting the minimum September of the 2023. And you can see that within the 30 ensemble members, which are represented by shading above and below the blue line ensemble mean. We have some results that are covering the NSIDC estimate the minimum of 4.2 million square kilometer relative to our ensemble mean about 4.7. So the different ensemble mean about half a million square kilometer. Those results are available since January 2019. Every month we run roughly a 30 ensemble member forecast up to 6 months. So currently we have the latest one on January 24 initialized, and our forecasts are extended all the way to end of July 2024. I recommend you check that website if you're interested. So we also did the longer term downscaling. So basically we're using the predictions from the Earth system model, like the NCAR, the US NCAR CSM2, and we use the atmospheric output from that model to drive our regional RASM model along the lateral boundaries. This is showing a 10-year time series comparison between the CSM in blue and the RASM in red. And basically the take-home message here is that the CSM starts very low in terms of the ice thickness, which is shown here in the on the right in the upper panel, where the shading is the ice thickness. Way too thin ice on September 2017, and somehow it seems like RASM over CSM increases the ice thickness over a 10-year period, versus RASM actually decreases thickness and area relatively in agreement with observations. The take-home message is that dynamical downscaling of the initialized CSM DPLE using RASM allows the RASM physics to dominate at the surface, which doesn't carry the CSM apparent biases shown by this increasing volume over a 10-year period. Similarly, we did something similar with the U.S. Department of exascale energy Earth system model, E3SM. We have a version of the E3SM Arctic with the grid refinement over the Arctic region, and we use the output from that model to force our RASM regional model over a 50-year period. And here on the left, I'm showing a time series over the volume. The blue is this E3SM Arctic ice volume over 50-year period. The gray shading is the observed or reanalysis estimated range of the ice volume from the Pyomas model, and the red time series here shown below. It's the CSM downscaling ice volume. So you can see that we have a very similar results compared to the CSM downscaling with the E3SM downscaling, that RASM physics dominate the surface because it's a fully coupled model, and we do not carry the apparent biases from the global Earth system model, which was also the case with the ANSEP CFS as well. So in general, when we compare the global system models in terms of the ice edge error and edge error, total ice edge error, the models vary in terms of the error between 1.25 roughly million square kilometer error during the winter time up to 3 million square kilometer during the melt season, versus RASM shown here in blue still has some biases, but significantly outperforms the Earth system model in terms of that metric. So to summarize, I just wanted to say that RASM is a semi-operational, fully coupled regional climate model. The output from that model has been used by the National Ice Center and the Mosaic operational fields, and as well as the submarine operations in the Beaufort Sea during 2020 and 2022. It provides the benefits of high-resolution, polar-optimized physics and computational costs for synthesis of limited observations, allowed resolving observed extreme events in space and time, in atmosphere, ocean, and sea ice, is readily available for further process level physics improvements. And the bottom line is that dynamical downscaling using a fully coupled regional Arctic system model represents a gain in terms of more realistic sea ice thickness distribution, provides physically consistent initial conditions, which appear relevant for up to decadal prediction, finally demonstrate potential for improved subseasonal to decadal predictive scale of relevance to Arctic stakeholders. And we're ongoing with very rigorous evaluation of the model and predictive skill. Thank you very much.
Wisław, thank you very much. Thank you for your flexibility and for your patience. Don't go away because we do have some time if there are questions. I'm not going to be the only person asking questions. So I think I've got, so stay with us. I hope you're comfortable. I hope you're not like just stuck in a taxi cab somewhere or something. And
no, I'm okay. Thank you.
Good, good. All right. And I'm going to have a helper with microphones. Yep. Do you mind? Do we have any questions? There's got to be questions. I've got questions, but you're not here to listen to me. Questions over here? Yeah? Right here. Somebody has a question.
Yes, but I have the microphone. My question was for, is it Lori? I might have, yes, ma'am. Lucy, okay. All right, I got like 1/4 of that correct, then failing. When you were looking at your research, I was thinking about the nature of sea ice and how it's changing, and I'm wondering if in the process, were you able to discern whether not just the concentration of ice, but the way it's different, it's thinner, it changes over the season. Does that impact what the ships were doing or affect what you had going on?
Thank you so much for that question. Because we focused just on September and we really split the ice into two categories, marginal ice zone and pack ice, we didn't look at that. But I think that would be really interesting to look at. I appreciate that feedback. And if you have a suggestion as to where those data might be, we would love to include it. So thank you.
All right, other questions? Oh, come on. There's questions in the back, 2, 3. This is like an auction.
Thank you. I have a question to Kelsey, right? It's about, so you mentioned that there was no much progress in terms of research on oil spills and on the sea ice, but to my knowledge, there was a quite substantial analysis from this project led by Zonke Maus from Norwegian University of Science and Technology, who did experiments in lab and field by spilling oil under the ice and investigating its permeability and how the oil kind of goes up. So my question is like, is it just, do you mean that it's just different scales, or what exactly you think why this is maybe not relevant for your research? Thank you.
No, that's a completely fair question. The purpose of the research really changed the character there. What a first responder needs to be able to do is look at the ice and know, am I going to deal with oil that is going to be spread by the current and it's going to drift far, or am I going to deal with a scenario where the ice is just a rubble field underneath and it's going to become encapsulated? And so creating the connection between the subsurface to the surface was really the point of the research. We have such good experiments on oil spill spreading under ice and flume-based experiments, but to provide the operator and the first responder the ability to just look and ballpark it was kind of the little twist. So yeah, no, totally, 100%. I'm on board with where you're going.
Thanks. We're kind of running out of time, and I told you there'd be some teasers, but I know that I think we have time for one more question. If there's one more kind of short, and you're already mic'd up, go ahead.
I'll try to keep it short. Okay, so this is for Anna, actually, Abby Tingstad, Center for Arctic Study and Policy at the U.S. Coast Guard Academy. I really appreciated your social science focus, kind of rounding out the session methodologically. I'm curious, when you hopefully get to do this work looking at tourism in those 3 countries, what would you focus on particularly as the great area of greatest concern for moving policy forward and regulations forward when it comes to tourism? Thank you.
Wow, thank you. I think there are several issues. my concern is that the discussion around stricter regulations, like the last official Norges offentlige utredninger talked about in their special cruise plan, and there are planned to restrict, especially the larger ships are using heavy crude oil, so it's on fuel-based restrictions, that these will remain as a discussion because the economic interests at stake are really high, and the infrastructure capacity that has been built to accommodate this type of visits is an investment that local authorities would like to get back. So I think that we need to maybe bring this discussion up to a national level, and I would also like to doubt that local authorities can be expected to take such drastic decisions that need to be made, especially around the much larger ships. And I want to add to that unfortunately we have fantastic data that has been produced in recent decade, for instance from PAME, but they're all on a very aggregated level, and there's no distinction made between the smaller ships that may be very feasible and the much larger ship on environmental impacts. So yeah, I think I'll keep it at that.
Thank you very much. A big thank you to all of our presenters today. Just a wealth of knowledge, a wealth of research. As a policy, non-science person, I've learned a lot. I hope that you have as well. We started today with a quote, with a theme from Taylor Swift. And you might think that this is ridiculous, but we're going to end with Taylor Swift. And that is, if you fail to plan, you plan to fail. You know the lyrics from Mastermind, don't you? If you fail to plan, you plan to fail. And let's carry that forward from all of the hard work that's been done here today. Could we please have another round of applause for all of our presenters? Wisla, thank you online as well and your flexibility. I wish all of you a wonderful rest of Arctic Frontiers, and thank you very, very much for coming. Bye-bye.